Welcome back, focused learners. I am absolutely pumped to be your coach today for this explainer. We are locking right in on Lesson 03, our assessment rehearsal for ratios and statistical claims. Now, do me a favor and leave the complex algebra systems in geometry right at the door. Today? Well, today is all about proportional reasoning and data logic, so you can absolutely crush this assessment.
Here's our rehearsal plan for today. We're going to kick things off with Level A, Ratio Basics, then move right into Level B, Graphs and Tables. After that, we'll tackle avoiding common ratio traps, take on the real-world data challenge, and finally, wrap it all up with the reasonableness check.
All right, Section 1, Level A, Ratio Basics. Let's dive right into this warm-up round.
Okay, so before we actually solve anything, we gotta grab our toolkit, right? A ratio, at its core, is just a comparison of two quantities. That's it. And when we scale those quantities up or down perfectly, we get what's called equivalent ratios. They look like different numbers, but they hold the exact same value. And the magic happens when you set two of those ratios equal to each other. Boom! You've just built a proportion.
Let's actually ground these abstract ideas into something relatable. Say, back-to-school shopping. Imagine this. 4 notebooks cost $6. Bam! That right there, that's our starting ratio. We're literally just comparing 4 items to $6. Now, we can take that starting ratio and stretch it out. Like if we double the notebooks to 8, we just multiply the cost by 2 as well, which gets us $12. Makes sense, right? But honestly, the most powerful move here is dividing. If we divide those 4 notebooks by 4, we get down to just 1 notebook. Do the same to the money, divide $6 by 4, and we hit the golden number, $1.50. That is our unit price. And let me tell you, once you have the unit price, you hold the key to finding the cost for literally any amount.
Moving on to Section 2, Level B, Graphs and Tables. Time to structuring our data.
So let's expand that math vocabulary a bit. You've got a rate, which is honestly just a special kind of ratio that compares quantities with totally different units. We're talking dollars in notebooks, miles in hours, or, price per pound. Then there's the unit rate, which we actually just found. It's the rate for exactly one of something, meaning it has a denominator of 1. And finally, when we want to take these relationships and scale them up or down, say on a map or a blueprint, we use what's called a scale factor as our multiplier.
All right, I want you to just pause and think for a quick second. Look closely at the data we're about to see and ask yourself, is this relationship truly proportional? And more importantly, how would you actually prove it?
Okay, so this right here brilliantly illustrates exactly what a perfect proportional relationship looks like in the wild. Look at those x and y values. Notice anything? Every single time you divide the output y by the input x, you get the exact same number, 4. 4 divided by 1 is 4, 8 divided by 2 is 4, 12 divided by 3 is 4. Because that multiplier stays perfectly constant, we know for sure this is a proportional relationship. Our constant of proportionality is 4, which leaves us with the super clean equation y equals 4x.
Now, let's contrast that just to make things crystal clear. A true proportional relationship, written out as y equals kx, must always start at 0. Think about it. If you buy 0 pounds of apples, you pay exactly $0, right? On a graph, it passes perfectly through the origin. But take a look at a non-proportional linear relationship. Say you jump in a taxi that charges $2 per mile. Sounds simple, but wait, they also hit you with a $4 fee just for getting in the car. Because that cost starts at 4 instead of 0, it's still linear, like it makes a straight line on a graph, but it is absolutely not proportional.
All right, on to Section 3, Avoiding Common Ratio Traps. Welcome to the trap room, folks.
Here is the first trap on the board. A lot of people out there think ratios can only compare things that have the exact same units, like inches to inches. Well, I'm here to tell you that is totally false. Rates are actually incredibly useful ratios, specifically because they compare different units. Dollars per pound, miles per hour, cost per notebook, you get the idea. So whatever you do, do not let different units scare you off.
Okay, really watch out for this next trap, because it's a classic visual illusion. Your brain sees a larger numerator and immediately screams, oh, that's definitely a bigger ratio. But here is the truth. A ratio's actual value is entirely dependent on its relationship to the denominator. You just can't judge a ratio by its top number alone. It's mathematically dangerous.
Let me show you exactly how this works with a real example. Imagine you're pulling colored tiles out of a bag. If you have 3 winning tiles out of 10 total, your probability is 3 out of 10. Simple. Now, imagine a second bag,
But this one only has one winning tile out of 2. Now sure, the number 3 is obviously bigger than the number 1. But look at the actual percentages. 3 out of 10 is only a 30% chance. But 1 out of 2? That's a 50% chance. So that 1 out of 2 ratio is actually way larger. Always check the whole picture.
And that brings us to Section 4, Challenge, Real-World Data. Get ready, because this is the boss level.
Now, to decode real statistical claims, we really need to understand where the data is coming from. A sample is just a small chunk of the overall population that we actually bother to measure or survey. And a data display, that's simply how we visualize that sample, whether it's through graphs, tables, or scatter plots. But here's the thing you gotta remember. Statistics uses data to make big claims, but the quality of any claim entirely depends on how that sample was collected in the first place.
So here's your 3-step attack plan for literally any data claim you see on your assessment. Step 1, check the sample for bias. Like, is it truly representative of the whole group? Step 2, break the math down to the unit rate so you can find the real constant. And step 3, justify your conclusion. Look closely at the data display and ask yourself, is this comparison actually fair based on the math? Prove it.
Let's test that plan right now. Check out this scenario. The school needs to decide how to spend the new sports budget, so they conduct a survey, but they only ask the basketball team. I want you to apply our steps here. Why is this claim just hopelessly broken? Give it a thought. Yep, you nailed it. It fails step 1 immediately. It is a heavily biased sample. By only asking the basketball team, it completely overrepresents students who already care deeply about one specific sport. It entirely fails to represent the actual whole school population.
All right, home stretch. Section 5, the reasonableness check. Time to lock in that mathematical mindset.
We like to call this the reasonableness check. See, getting a number at the end of a long, stressful calculation, that isn't actually the end of the math. The real goal is taking a step back and evaluating whether that number makes logical sense back in the real world. You gotta ask, does the story actually match the stats?
So, here is your final mental checklist before you ever hand in an assessment. First, did I actually answer the specific question asked, or did I kind of just stop halfway? Second, are my units right? Because giving a naked number without units means literally nothing. Are we talking dollars, items, miles? Third, does the sign make sense? Like, if you're calculating a discount on a t-shirt, you definitely shouldn't end up paying more than the original price. And finally, if it's a data question, is the sample actually representative of the population? I really want to leave you with this final vital question. Does your final answer actually make sense in the real world? Remember, math is a tool we use to understand our reality. It's not just a bunch of abstract numbers floating on a page. You guys have absolutely powered through proportional relationships and data reasoning today. So the next time you see a statistic flashed on the news or a deal in a store, ask yourself, are they really showing you the whole picture? Take this critical analytical mindset right into your assessment, and I promise you will crush it. Keep learning, keep questioning, and I'll catch you on the next explainer.